Riemann Curvature Tensor. In this chapter we derive the Riemann Curvature Tensor, the very foundation of the left-hand side of Einstein's field equations. From here on, we'll simply call it the curvature tensor. This tensor expresses as a mathematical equation Einstein's core idea in general relativity. The curvature of spacetime is the true nature of gravity. We'll derive the curvature tensor using two independent methods: the concept of parallel transport and the algebraic approach of taking covariant derivatives twice. Let's begin with the more intuitive method, parallel transport. What is curved space? Earth example. What properties does a curved space have? Let's start with a broad intuitive example. Consider the surface of the Earth, a two-dimensional sphere. There are two vectors at 2 points on the equator, equal in size and pointing in the same direction. Let's send them off toward the North Pole, moving them in parallel. This method of movement is parallel transport of a vector, moving it straight, without changing its size or angle at each point. In other words, an operation that makes the covariant derivative zero. At first, the two vectors stay parallel, but they gradually converge and end up crossing at the North Pole. Their size stays exactly the same, but their direction changes. This is a property of curved space. The equation that expresses the difference between these two vectors is the curvature tensor. If the difference is zero, the space is flat. If it is not zero, the space is curved. Deriving the Riemann curvature tensor, setting the stage. Up to this point, we've considered covariant derivatives and parallel transport in a general space, without specifying its dimension. From here on, we finally turn to the stage of four-dimensional spacetime itself, our own universe, to derive the curvature tensor. Based on the considerations above, let's derive the curvature tensor using parallel transport. Within four-dimensional spacetime, using two parameters u and v, consider a two-dimensional surface given by x mu equals x mu of u, v. This notation means that each component of the four-dimensional spacetime coordinate x mu equals 0, 1, 2, 3, is expressed as a function of the two parameters u and v, specifically x0, x1, x2, and x3, each given as functions of u and v. On this surface, let's take a two-dimensional, infinitesimally small closed parallelogram. We'll label its four vertices as O, 0, 0, P, delta U, 0, Q, 0, delta V, and S, delta U, delta V. Let's consider transporting a vector in parallel along two different paths within this infinitesimal region. The direction of the vector at the starting point is arbitrary, but it's the same for both paths. One is OPS, we'll call this path C1. The other is OQS, we'll call this path C2. Both paths start from the same point O, and arrive at the same final point S. But the order in which they move differs. Along path C1, we first move delta U in the U direction, and then move delta V in the V direction. Along path C2, we first move delta V in the V direction, and then move delta U in the U direction. In curved space, a direction that started out the same at the origin ends up as a different direction at the final point S, due to this difference in order. This is a property that naturally emerges in curved space. Why does this derivation give us the curvature tensor? Parallel transport is a movement that makes the covariant derivative zero. In other words, the change in a vector's size and angle is zero. In flat space, no matter which order you transport a vector along two different paths, The direction of the vector at the final point matches exactly, and the difference is zero. But as we saw with the example of the Earth's surface, no matter how carefully we transport a vector without changing its size, its direction inevitably changes. This is a characteristic of curved space. With a single path alone, there's nothing to compare it to, so we can't determine how much the direction has changed. That's why we take two paths, reverse their order, and take the difference. If that difference is non-zero, we can conclude that this spacetime is curved. The equation that expresses this is the curvature tensor. It represents how curved spacetime is. Let's now express this idea in the form of an equation. Derivation of the C1 path. Let's first find the equation for the C1 path. This is the path where we parallel transport by delta U from the origin O to P, and then by delta V to S. Using the definition of parallel transport as a reference, let's find the equation for O to P. Similarly, the equation for P to S is. Therefore, the equation for parallel transport along the C1 path is. Our goal is to express the values at P in this equation in terms of the values at the origin O. This is because we want to show that the vectors from the C1 path and the C2 path, which pointed in the same direction at the starting point O, end up pointing in different directions at S, by taking their difference. So we will convert the four quantities on the right-hand side: 1, a, mu of p parallel, 2, gamma mu tau rho of p, 3, a, tau of p parallel, 4, delta x rho of p, all into values at O. 1. We have already found a, mu of p parallel. 3. Let's find a, tau of p parallel, based on this as well. 4. Let's convert delta x rho of p into a value at O. Step 0. To do this, we first approximate an arbitrary point x mu, u, v, on the u, v plane to first order, as a general formula, by Taylor expanding it around the origin O, 0, 0. This will serve as a common tool that we will use repeatedly going forward, whenever we need to find the coordinates of S, P, or Q. Step 1. Let's apply this formula to S and P. Applying it to S, delta U, delta V, substituting U equals delta U, V equals delta V. Applying it to P, delta U, 0, substituting U equals delta U, V equals 0. The term in the V direction vanishes. Therefore, evaluating delta x rho of P along the C1 path at the origin O, we obtain the following. Here, the subscript, u, in x rho sub u at O represents the displacement in the u direction from O to P, with delta V equals 0, meaning there is no displacement in the V direction. Next, with an I towards substituting x rho sub u at O into 1 and 3 later, let's write it in the following form. Step 2, specific to C1, deriving delta x rho of P. Since the displacement from P, delta u 0 to s delta u delta v is purely in the v direction, we apply the same general formula again, but this time based at p, with respect to v only. Therefore, Step 3. Expanding the coefficient, partial x rho, partial v, at delta u, 0 in terms of quantities at O. This coefficient itself is not yet expressed in terms of O, so we expand it one more step, with respect to u. Giving us the final result. Deriving gamma mu tau rho of p. Step 0. The general formula for gamma mu tau rho. In the neighborhood of the origin O, i.e., u v equals 0, 0, let's Taylor expand gamma mu tau rho at an arbitrary point, u v, reducing it to x via the chain rule. From the general formula for x mu. Step 1. Deriving 2. Gamma mu tau rho of p, applying it to p, substituting delta u, v equals 0. Now that we have expressed all quantities at p, in terms of quantities at O, all that remains is to substitute them. We have now substituted 1 through 4 into the equation. From here, the calculation continues as we expand and organize this expression, so please pause the video and check it at your own pace. This is the equation for parallel transporting the vector a mu along the C1 path. Next, we will derive the corresponding equation for the C2 path in the same way, and then take the difference between the two. Derivation of the C2 path. Next, we will derive the C2 path, which is O, 0, 0, to Q, 0, delta V, to S, delta U, delta V. This path is analogous to C1, but with the order of the U and V translations reversed. It first translates by delta V, then by delta U. Because of this, we can obtain the equation for C2 simply by swapping U and V in our previous derivation. Below, we show all the steps, so if you'd like to check them carefully, please pause the video. If you just want the result, feel free to skip ahead to the slide titled The C1 Path and the C2 Path. Derivation of the C2 path. Let's find the equation for the C2 path. This is the path where we parallel transport by delta v from the origin O, 0, 0, to Q, 0, delta v, and then by delta u to S, delta u, delta v. Using the definition of parallel transport as a reference, let's find the equation for O to Q. Similarly, the equation for Q to S is. Therefore, the equation for parallel transport along the C2 path is. Our goal is to express the values at Q in this equation in terms of the values at the origin O. This is because we want to show that the vectors from the C1 path and the C2 path, which pointed in the same direction at the starting point O, end up pointing in different directions at S, by taking their difference. So we will convert the four quantities on the right-hand side: 1, a, mu of Q parallel; 2, gamma mu, tau rho of Q; 3, a, tau of Q, parallel; 4, delta x rho of Q, all into values at O. 1, we have already found a, mu of Q, parallel. 3, let's find a, tau of Q, parallel based on this as well. Four, let's convert delta x rho of Q into a value at O. Step 0. To do this, we first approximate an arbitrary point x mu, u, v, on the u, v, plane to first order, as a general formula, by Taylor expanding it around the origin O. This will serve as a common tool that we will use repeatedly going forward, whenever we need to find the coordinates of S, P, or Q. Step 1. Let's apply this formula to S and Q. Applying it to S, delta U, delta V, substituting U equals delta U, V equals delta V. Applying it to Q, 0, delta V, substituting U equals 0, V equals delta V. The term in the U direction vanishes. Here, the subscript V in delta x rho sub V of O represents the displacement in the V direction from O to Q, with delta U equals 0, meaning there is no displacement in the U direction. Next, with an eye towards substituting delta x rho sub V of O into 1 and 3 later, let's write it in the following form. Step 2. Specific to C2, deriving delta x rho of Q. Since the displacement from Q, 0, delta V, to S, delta U, delta V, is purely in the U direction, we apply the same general formula again, but this time based at Q, with respect to U only. Therefore, Step 3. Expanding the coefficient partial x rho partial U in terms of quantities at O. This coefficient itself is not yet expressed in terms of O, so we expand it one more step, with respect to V. Giving us the final result. Two, deriving gamma mu tau rho of Q. Step 0. The general formula for gamma mu tau rho. In the neighborhood of the origin O, i.e. U, V equals 0, 0, let's Taylor expand gamma mu tau rho at an arbitrary point, U, V, reducing it to x via the chain rule. from the general formula for x mu. Step 1. Deriving 2. Gamma mu tau rho of q. Applying it to q, substituting u equals 0 delta v. Now that we have expressed all quantities at q in terms of quantities at O, all that remains is to substitute them. From here, the calculation continues as we expand and organize this expression, so please pause the video and check it at your own pace. This is the equation for parallel transporting the vector, A, mu along the C2 path. The C1 path and C2 path. As you can see, this is simply the argument for C1 with U and V interchanged. Now that we have the equations for parallel transport along both paths, we can take their difference. In this case, we calculate OQS via path C2 minus OPS via path C1. This is called the Riemann Curvature Tensor. It forms the backbone of the left-hand side of the Einstein field equations in general relativity. The difference between the contravariant vector components parallel transported along the two paths is given by the following equation. Why do the higher-order terms vanish? In deriving the C1 and C2 paths, we stated that we discard terms of third order or higher. However, this is not simply because these terms are small. Here we show step by step why these terms vanish through a rigorous procedure. We start from the equation already derived, with the higher order terms added back in. Part 1. Why pure single variable, higher order terms cannot exist. Consider. We will show that the O of delta U squared and O of delta V squared terms in this equation are 0. What would happen if delta U equals 0? In that case, the C1 path, OPS, collapses, since P equals 0, 0 equals O, into effectively just O to S, a displacement purely in the V direction. Likewise, the C2 path, OQS, collapses, since S equals 0, delta V equals Q, into effectively just OQ, also a displacement purely in the V direction. In other words, when delta U equals 0, both C1 and C2 collapse into the exact same single path moving purely in the V direction from O. Since they follow the identical path to the identical destination, the results of parallel transport must agree exactly. Therefore, by exactly the same argument, when delta V equals 0, this fact follows purely from the geometric structure of the paths, without any algebraic computation. And from this fact, we can conclude the following: if we expand delta A mu as a polynomial in delta U and delta V, any term containing only delta U, with no delta V, or only delta V, with no delta U, must have a coefficient of exactly 0. If this were not the case, substituting delta V equals 0, or delta U equals 0, would leave a non-zero term behind, contradicting the identical vanishing we just established. Example: if O of delta U squared remained when delta V equals 0, with the delta U delta V and O of delta V squared terms crossed out, since both vanish when delta V equals 0, leaving only O of delta U squared, which cannot be allowed to survive. Part 2: The terms that do remain. From the argument in Part 1, we now know that the only terms that can survive in the expansion of delta A mu are ones containing both delta U and delta V. Expanding it out, the lowest order surviving term is delta U delta V. This is the curvature tensor component itself, while higher order terms of the form O of delta U delta V times delta U plus O of delta U delta V times delta V also remain. Writing these terms out concretely, they take forms such as delta U squared, delta V, or delta U, delta V squared. The coefficients themselves are complicated combinations of gamma, but we only need to pay attention to the degree. These terms are not eliminated by the argument in Part 1 alone. Here, we follow the procedure of dividing and then taking the limit. That is, we divide by delta U delta V, and then take the limit delta U delta V, and then take the limit, delta U approaches 0, delta V approaches 0. Let's show this concretely. Here, C1, C2, C3, C4 denote, in shorthand, complicated coefficients made up of gamma and its derivatives. Dividing this by delta U delta V. And taking the limit. What remains is in this way, through a rigorous procedure, the higher-order terms vanish from the noncommutativity of parallel transport, and only the components of the curvature tensor are legitimately extracted. We derived the Riemann curvature tensor from the difference in parallel transport along two paths, but this can also be understood in the following way. By taking OQS minus OPS, we are effectively transporting a vector around a closed infinitesimal loop. OQSPO, starting and returning to point O. If R is non-zero when we return to the original point O, we can conclude that spacetime is curved at that point. If R equals 0, we can say that spacetime is flat at that point. A note on the Riemann curvature tensor. In this derivation, we obtain the curvature tensor by taking the difference of the parallel transport paths as C2 minus C1. If we instead take the reverse order, C1 minus C2, the sign of the curvature tensor will be flipped. This is why the sign convention for the curvature tensor varies across different references. Derivation of the Riemann curvature tensor via covariant derivatives. We will now derive the curvature tensor using covariant derivatives. This method also has important significance. We take the covariant derivative of a contravariant vector twice in different orders, and then take their difference. Let's consider nabla rho, nabla nu a mu. We need to determine what type of tensor's covariant derivative this expression corresponds to. First, focusing on what's inside the parentheses, we see that it is the covariant derivative of a contravariant vector taken once. The covariant derivative nabla nu a mu, as a whole, is a mixed tensor with one contravariant index mu and one covariant index nu. Therefore, looking at the entire expression, this is equivalent to the covariant derivative of a mixed tensor. Second covariant derivative of a contravariant vector. We substitute the expression for the covariant derivative of a contravariant vector into the parentheses. Here, we're working through the calculation for the second covariant derivative, so feel free to pause and follow along at your own pace. Let's interpret the physical meaning of this expression intuitively. First, we find how a mu changes as we take a small step in the x nu direction. Then, we find how this resulting quantity changes as we take a small step in the x rho direction. Next, let's consider the reverse order. From here, we're working through the calculation in reverse order, differentiating a mu with respect to rho first, then nu. Feel free to pause and follow along at your own pace. By taking the difference between the two second covariant derivatives, computed in reversed order, the Riemann curvature tensor emerges. Comparing the two curvature tensors. We compare the Riemann curvature tensor derived from two covariant derivatives with the curvature tensor derived from parallel transport, C2 minus C1. Let's rename the indices, tau to lambda, rho to nu to rho, and the dummy index lambda to alpha. We see that this is exactly the same expression. In other words, the Riemann tensor obtained from the covariant derivative order nabla rho nabla nu a mu minus nabla nu nabla rho a mu matches, with the same sign, the Riemann tensor obtained by taking the difference between the C2 and C1 paths in parallel transport. Let's consider what this means. What the indices of the Riemann curvature tensor, r, mu lambda nu rho mean. We took the covariant derivatives in the following order. Each covariant derivative has the following meaning. Nabla nu. The operation of moving by dx nu in the new direction. Nabla rho. The operation of moving by dx rho in the rho direction. Just as in the case of parallel transport, this means traversing a small square region once around, in the order nu, then rho, then minus nu, then minus rho. Lambda represents the vector being transported. Nu and rho represent the order and the region of the loop. And mu represents the component of the difference in direction between the start and the goal. Noncommutativity of the Riemann curvature tensor. We took the covariant derivatives in this order. Nabla rho nabla nu a mu minus nabla nu nabla rho a mu. We express this as follows. This is called the noncommutativity of the Riemann curvature tensor. It means that in curved spacetime, if we take the difference between the covariant derivatives applied in reversed order, going around an infinitesimal loop, and the result is non-zero, then that spacetime is curved. This is an unavoidable property of curved spacetime, no matter how carefully we parallel transport a vector, keeping its magnitude and angle unchanged, setting the covariant derivative to zero. Once we go all the way around a loop, the direction of the vector at the start and the goal will differ. This is the equation expressing that fact. Correspondence between noncommutativity and parallel transport. Let's try reversing the order of the covariant derivatives, swapping rho to nu. This corresponds to swapping the lower indices nu and rho of the Riemann curvature tensor. Antisymmetry of the Riemann curvature tensor. Comparing these two expressions, the signs are completely reversed. This shows that the Riemann curvature tensor obeys the following rule when the second and third lower indices are swapped. R mu lambda nu rho equals minus R mu lambda rho nu. This corresponds to traversing the reverse path, from C1 to C2, in parallel transport. Two roads to the same curvature. In this way, we have shown that the Riemann curvature tensor can be derived in two entirely independent ways, through parallel transport, and through the commutator of covariant derivatives, and that both approaches yield exactly the same tensor. Whether you walk around the loop with a vector, or subtract the order of differentiation, curved spacetime always leaves the same signature behind. Riemann curvature tensor. The only tensor that reveals the curvature of spacetime. We will compute concrete examples of the Riemann curvature tensor in Euclidean space, Cartesian coordinates, polar coordinates, and in Riemannian space, a two-sphere, and examine more deeply what it physically means. 1. The curvature tensor in Cartesian coordinates. Let's first find the curvature tensor in Cartesian coordinates. The Christoffel symbols were given by The Christoffel symbols represent the amount by which the basis vectors change, and are built from the metric, the inner product of the basis vectors. In Cartesian coordinates, the basis vectors do not change anywhere throughout space. Therefore, all the Christoffel symbols vanish, and consequently the curvature tensor also vanishes. (2) The curvature tensor in polar coordinates. To find the curvature tensor in polar coordinates, we first need to derive the Christoffel symbols. Since the parameters of polar coordinates are r, theta, there are 2 to the third power equals 8 components of gamma. We will use Einstein's summation convention, so let r equals x1, theta equals x2. Let's find the metric tensor for polar coordinates. The position vector in Cartesian coordinates is expressed as express x, y in polar coordinates. Substituting. Take the partial derivatives of the position vector with respect to r and theta to find each basis vector, unnormalized. Now that we have the basis vectors, let's derive the metric, the inner product of the basis vectors. Here, we are explicitly finding the covariant metric tensor in polar coordinates. Please pause the video and check it at your own pace. Matrix representation. Let's find the contravariant metric tensor from the covariant metric tensor. These metrics have a Kronecker-delta relationship, that is, they are inverse matrices of each other. Also, G mu alpha equals G alpha mu. We use these facts. Here, we derive the contravariant metric tensor using the properties of the Kronecker delta and the inverse matrix. Please pause the video and check it at your own pace. Christoffel symbols in polar coordinates. We cross out the zero components of the metric and the derivatives of constants, which equal 0, and find each Christoffel symbol. Here, we find all the components of the Christoffel symbols in polar coordinates. Please pause the video and check it at your own pace. The Riemann curvature tensor in polar coordinates. Non-zero Christoffel symbols. We will now find the Riemann curvature tensor for polar coordinates. The parameters are r, theta equals x1, x2. We will cross out any term that is 0, or that becomes 0 upon differentiating a constant. Here, we derive all the components of the Riemann curvature tensor in polar coordinates. Please pause the video and check it at your own pace. What the result for polar coordinates means. Although the Riemann curvature tensor for polar coordinates turned out to be entirely zero, some of the intermediate Christoffel symbols were non-zero. Let's consider what this means. Coordinates are simply drawings imposed on the canvas of space for human convenience. Changing the coordinate system does not change the shape of space itself. That's why, for a plane, 2D Euclidean space, no matter how curved a coordinate system we draw, the underlying space is flat, so the Riemann curvature tensor is zero. This is because the Riemann tensor represents an intrinsic property, how curved the space itself is, that does not depend on the choice of coordinate system. The Christoffel symbol is a physical quantity representing the change of the basis, defined by partial a nu partial x sigma equals gamma lambda sigma nu a lambda parallel transport of vectors. 3. Polar coordinates are drawn along the radial direction r and the angular direction theta counterclockwise and are not normalized. In this case, the polar coordinate basis vectors, the radial and angular basis vectors, themselves change direction and length depending on location. Because the basis changes, non-zero Christoffel symbols appear. Let's look at an illustrative diagram. This diagram is exaggerated for clarity. Gamma r theta theta represents the r component of how much the basis vector e theta, blue, changes when moved along the theta axis. Gamma theta theta, r, represents the theta component of how much the basis vector e theta, blue, changes when moved along the r axis. Gamma theta r theta represents the theta component of how much the basis vector e r, green, changes when moved along the theta axis. The Riemann curvature tensor was built from the necessity that, in a curved space, a vector transported around a small closed loop, starting and ending in the same direction, ends up pointing in a different direction upon return. No matter how curved the coordinate lines of polar coordinates appear, the underlying space is flat, so this is nothing more than an apparent distortion of the coordinates. In fact, this can be seen immediately from the principle of general covariance, without any calculation. The coordinate transformation law for the Riemann curvature tensor is given as follows: Part 14, Tensor Coordinate Transformation Laws, 2. This is a concrete instance of the principle of general covariance, that a tensor equation holds in the same form in any coordinate system. R mu lambda nu rho also follows the pattern of the transformation law for P, Q type tensors that we confirmed in Part 14. Given this, the conclusion, if R, alpha beta gamma delta is 0 in Cartesian coordinates, then it is 0 in any coordinate system, follows directly from the definition of the tensor itself, with no additional calculation required. Up to now, we've emphasized that in curved spaces, since the basis differs from point to point, the concepts of parallel transport and covariant differentiation become essential. To avoid overcomplicating the discussion, we deliberately did not mention it earlier, but there are cases even in Euclidean space, such as polar coordinates, where the Christoffel symbols are non-zero. What we can conclude from this is, the Christoffel symbols being zero does not mean the space is not curved. Only when the Riemann curvature tensor is non-zero can we assert that a space is curved. And, as mentioned at the outset, this Riemann curvature tensor is precisely the foundation of the equation that expresses the curvature of spacetime, establishing Einstein's field equations. Next, we will use the concrete example of a two-sphere to confirm that in a curved space, the Riemann curvature tensor does not vanish. The Riemann curvature tensor for a two-sphere. We found the covariant metric tensor for the two-sphere in Part 15, Parallel Transport of Vectors, 1, of this series. R is a constant. Since the contravariant metric tensor is the inverse matrix of the covariant metric tensor, it is as follows. Next, let's find the Christoffel symbols. To use Einstein's summation convention, let theta, phi, 2, x1, x2. Since the parameters of the two-sphere are theta and phi, each index can take two values, so there are 2 to the third power equals 8 Christoffel symbols. We will cross out any term that is 0, or that becomes 0 because it is the derivative of a constant. Here, we find all the components of the Christoffel symbols for the two-dimensional sphere. Please pause the video and check it at your own pace. The Riemann curvature tensor for the two-sphere. The Riemann curvature tensor has four indices, but since we are in two dimensions, each parameter can take two values. So there are 2 to the fourth power equals 16 combinations. We will cross out any term that turns out to be 0. The Riemann curvature tensor for the two-sphere. Summary. We've confirmed that the Riemann curvature tensor for the two-sphere has non-zero terms. In other words, this space is curved. Let's use everything we've learned so far to clarify the path that led to this conclusion, and what it means. Let's consider this from the perspective of two-dimensional inhabitants. They decided to investigate whether the world they live in is flat or curved. To do this, they first need to grasp the overall picture. The blueprint for that is the metric tensor. Here, r is a constant, so for simplicity, let's set r equals 1. G theta theta equals e theta dot e theta equals 1, so the theta direction gradation is the square root of g theta theta, which is 1. Likewise, g phi phi equals e phi dot e phi equals sine squared theta, so the phi direction gradation is the square root of g phi phi, which is sine theta. Since g theta phi equals g phi theta equals e theta dot e phi equals 0, the inner product is 0, so the theta and phi sides of the quadrilateral meet at 90 degrees. We'll begin by filling the region using squares. The shape, size, of each quadrilateral is determined by the metric g mu nu, independently at each point. The inhabitants start out with only the coordinates, theta, phi, mere addresses. But an address alone doesn't tell them the actual distance to the next region. So they turn to the line element ds squared equals d theta squared plus sine squared theta d phi squared to begin measuring how much actual distance separates 2 points. For the inhabitants, ds squared is their one and only guide. It is a universal way of measuring that holds true regardless of whether space is flat or curved, and regardless of dimension. No matter how you change the coordinate system, the distance this line element tells you remains the same. This line element alone tells them the true distance in their world. Theta is the angle from the North Pole, 0 degrees at the North Pole, 90 degrees at the equator, 180 degrees at the South Pole. Phi is simply longitude, going all the way around from 0 degrees to 360 degrees. As they extend their measurements in every direction, they notice that the actual length of one unit of phi changes depending on location. The closer they get to the North Pole, the smaller theta becomes, the shorter the actual east-west distance becomes, until it reaches exactly 0 at the North Pole itself, theta equals 0. Let's actually calculate this. Here, we calculate how the length of the square's edge in the phi direction shortens as we move from the equator toward the North Pole. Please pause the video and check it at your own pace. Stage 1. Building a local ruler. First, the inhabitants move just slightly in the theta direction and the phi direction, right where they stand. Following ds squared equals d theta squared plus sine squared theta, d phi squared. Moving delta theta while keeping phi fixed. The actual distance is delta theta. This ratio is always 1, regardless of location. Moving delta phi while keeping a theta fixed. The actual distance is sine theta delta phi. This tells them the local ruler at the place where they're standing, how much actual length one unit is, in both the theta and phi directions. This is the 1 by 1 square or 1 by 0.5 rectangle we calculated earlier. Stage 2. Moving to the next region and measuring again. Using this local square as a guide, the inhabitants take one step into the neighboring region. There, they again use ds squared to measure the square, or rectangle, at this new location. Since the value of theta has changed, sine theta has changed too, so they notice that the phi direction width of the square changes from region to region. Stage 3. Repeating this to extend the map in every direction. They repeat this process, measure, take a step, measure again, in every direction, north, south, east, and west. In doing so, they notice that near the equator the squares line up neatly, while closer to the poles, the squares get increasingly compressed in the phi direction, turning into narrow rectangles. Next, using only their own coordinate system, with no knowledge of any outside world, they employ the Christoffel symbols to work out how the basis changes from place to place. The results are the gamma values we calculated. From the non-zero gamma, they learn that their space has a basis that differs from place to place. But at this point, they still don't know whether their space is actually curved. Let's look at the diagram of gamma. We've made a diagram of the Christoffel symbols for the two-sphere. Let's look at what happens starting from the bottom left. theta equals pi over 2, the equator, from our point of view. At first, it's a square. By the definition of gamma phi theta phi, the phi component of how much the basis vector E theta changes when it moves an infinitesimal distance along the phi axis is 0. Next, our two-dimensional inhabitant moves toward what we would call the North Pole. Near theta equals pi over 4, a discrepancy arises, gamma phi equals cosine theta over sine theta. A corrected quadrilateral is needed to account for this. Similarly, on the bottom right at theta equals pi over 2, gamma theta phi, the theta component of how much the basis vector E phi changes when it moves along the phi axis, is 0. Near theta equals pi over 4, a discrepancy arises, gamma theta phi equals negative sine theta cosine theta. A corrected quadrilateral is needed to account for this as well. Using the non-zero gamma, they correctly measure the distortion of each quadrilateral and correct it into its proper shape. In this way, they fill the entire region and complete their map. Now that the preparation is complete, they move on to computing the Riemann curvature tensor. They already know that this is the tensor that represents the curvature of space. We've already found the non-zero terms, but let's explain the meaning of the indices of the Riemann curvature tensor. R, theta phi theta equals sine squared theta. Here, the first lower index, phi, represents the vector being moved. The second and third lower indices, phi and theta, represent the region being circled. The first step is in the phi direction, followed by the theta direction. Next, they proceed in the negative direction. The component representing the direction of the discrepancy upon returning to the starting point, after going all the way around, is, in this case, the upper index theta. The 2D inhabitants explore the curvature and shape of their world. What do the non-zero Riemann tensor components on the two-sphere, r, theta, phi theta, equals sine squared theta, and r, phi, theta phi, equals 1, actually mean? And going a step further, can the 2D inhabitants come to know the shape of their own world using only their own dimension? As the culmination of our chapter on the Riemann curvature tensor, let's experience what the left-hand side of the Einstein field equations means, limited here to 2 dimensions, and with a method of derivation and a precise definition that differ from the real thing. Let's examine the two non-zero components of the Riemann tensor on the two-sphere, r, theta phi theta equals sine squared theta and r, phi theta phi equals 1. We'll start with r, theta phi theta equals sine squared theta. By plugging in specific values of theta, let's see what this Riemann tensor actually looks like on the two-sphere. From this concrete example, if we parallel transport a vector around a small square near the equator, theta equals 90 degrees, we get the largest deviation in the theta direction. As we approach the North Pole, theta approaches 0 degrees, the length of this square's edges in the phi direction keeps shrinking, so going all the way around produces almost no deviation in direction, and r, theta phi theta approaches 0 as well. Here, a couple of intuitive questions might come to mind. First question, when we computed the Christoffel symbols for the two-sphere, the value of gamma at the equator, where the Riemann tensor takes its maximum value, was 0, and the square there had the most regular, tidy shape, a 1 times 1 square. Doesn't this seem inconsistent? However, gamma describes how things change with respect to a particular choice of coordinates, a matter of human convention. It does not, by itself, represent the curvature of spacetime. It is the Riemann tensor that represents the true curvature of spacetime, a property that does not depend at all on how we choose our coordinates. Why is the deviation largest at the equator? The key lies in the actual physical size of the square. The line element on the two-sphere is ds squared equals d theta squared plus sine squared theta, d phi squared, with r equals 1, and the metric tensor is given by g theta theta equals 1, g theta phi equals 0, g phi theta equals 0, g phi phi equals sine squared theta. Here, d theta squared, movement in the vertical direction, corresponds to moving by d theta from the North Pole toward the South Pole. Since the component is g theta theta equals 1, this distance traveled is the same, d theta, no matter what latitude, which horizontal circle, you're standing on. Sine squared theta, d phi squared, movement in the horizontal direction, on the other hand, corresponds to moving by d phi from east to west. Here, the actual distance traveled depends on which latitude, theta, you're currently at. At the equator, theta equals pi over 2. Since sine squared theta equals 1, the angle you move through translates directly into the distance d phi. This is the largest possible circle, so the distance is long. Just next to the North Pole, theta approaches 0 degrees. Since sine theta approaches 0, no matter how large an angle and longitude you sweep through, no matter how large d phi is, the actual distance traveled is nearly 0. What the Riemann tensor represents, the deviation in the vector's direction after going around a loop, corresponds to the actual area of the square. This is precisely why the deviation is largest at the equator, where the area is largest, and why it goes to 0 at the North Pole, where the area shrinks to 0. As we'll see later, the reason the components of the Riemann tensor become 0 is that we're using the theta phi coordinate system. It is not because the curvature itself becomes 0. You might have the intuition that, since the square at the equator looked like the most regular, symmetric 1 times 1 square, with gamma equals 0, the deviation there should be small. But this is a misunderstanding that comes from conflating the symmetry of a shape with its actual size. In reality, what determines the curvature of space is the latter, how large that region actually is. The second question is the Riemann tensor really 0 at the North Pole? The answer is no, it is not. Why does r theta phi phi theta equals sine squared theta become 0? If we simply plug in the North Pole, theta equals 0, we do indeed get 0. But this comes from how we've chosen coordinates on the two-sphere, namely, theta, phi. We need to pay attention to the fact that the North Pole is a coordinate singularity. The polar coordinate system, theta, phi, itself breaks down at the north and south poles, a defect of this coordinate system, where the value of the longitude phi cannot be defined at the poles, or rather, takes on infinitely many values simultaneously. The value 0 that we've been seeing so far is nothing more than an apparent number, one that arose purely because our ruler, latitude and longitude, i.e., polar coordinates, happened to collapse at the North Pole. In fact, if we were to use a different, normal, coordinate system, one that works perfectly well even at the North Pole, the component computed in that coordinate system would, at the North Pole, show not something approaching 0, but a finite, properly meaningful, value. In other words, the result that the components of the Riemann tensor become 0 at the North Pole was not a physical fact about the curvature genuinely weakening, it was caused by a defect in the coordinate system itself. The precise scope of what being a tensor guarantees. The property that a tensor doesn't depend on the choice of coordinate system guarantees this. If all the components of the Riemann tensor are 0 in one particular coordinate system, then all its components will also be 0 no matter which other coordinate system you use to compute them. In other words, This guarantees that the yes-no question, is space curved or not, gives a consistent answer regardless of coordinate system. However, being a tensor does not guarantee that the specific numerical value of one particular component, something like r, theta phi phi theta, stays the same when you change coordinate systems. Quite the opposite. The individual numerical values of the components will, of course, change if you change coordinate systems. This has exactly the same structure as the familiar fact that the components of a vector change when you change coordinate systems, but the vector itself, as an entity, does not change. Gaussian curvature, finding a curvature that doesn't depend on the coordinate system. Here, as groundwork toward the Einstein field equations, we'll work out the Gaussian curvature and examine its relationship to the Riemann tensor. Recall that the Riemann tensor represents the deviation in direction that results from carrying a vector all the way around a loop in some particular direction. Gaussian curvature, meanwhile, is a notion specific to two dimensions. It expresses the degree of curving at a single point in a region, boiled down into one single number. On the two-sphere, the area of the square-shaped region differed from place to place, and so did the value of the Riemann tensor's components. The result of 0 at the North Pole, as we saw, arose from our choice of coordinates. In relativity, however, what matters are physical quantities that don't depend on the coordinate system. So here, we'll derive a curvature for the two-sphere that is independent of coordinates. Put roughly, since it's the difference in the area of the square-shaped region that causes the value to change from place to place, the idea is to divide the Riemann tensor's deviation for a given region by the area at that location, and in doing so, obtain a single, unified curvature for the space as a whole. The formula for Gaussian curvature. This is Gauss's discovery of the relationship between the Riemann tensor, the numerator, and the metric, the denominator, rewritten in the modern language of the Riemann tensor. And it was precisely Einstein's general relativity that extended the spirit of Gauss's discovery into the four-dimensional universe. The intuitive meaning of this formula is, if you want to know the actual degree of curving, the substance, take the apparent degree of curving, the Riemann tensor, and correct it by dividing by the distortion of your ruler, the metric. What the denominator, g theta theta g phi phi minus g theta phi squared, means. Geometrically, this combination of metric tensor components in the denominator represents a quantity related to the area of one small coordinate grid square at that location. We'll confirm exactly what this quantity is, in detail, shortly. Near the equator, one grid square is large and roomy. Near the North Pole, since the lines of longitude pinch together, one grid square becomes small and squashed. In other words, the denominator is a meter that measures how much the tick marks of the coordinate system you're currently using are being compressed at that location, the factor by which they're magnified or shrunk. Why does this become an area? Recalling the formula for the area of a vector parallelogram. Let's recall the formula for finding the area S of the parallelogram formed by two vectors A and B on a geometric plane. Using the dot product, the square of the area can be written as follows. Now, recall that the metric on the two-sphere was expressed in terms of the dot products of the basis vectors. Now, let's substitute the definitions of the dot products we saw a moment ago directly into the denominator of the formula, g theta theta g phi phi minus g theta phi squared. This is exactly the formula for the square of the area of the parallelogram formed by two vectors. In other words, the relationship g theta theta, g phi phi, minus g theta phi squared, equals the area of one grid square formed by the basis vectors, squared. Holds. Let's go ahead and compute the denominator. Since this is the square of an area, its units are meters to the fourth. What the numerator, r, theta phi phi theta, means. The Riemann tensor in the numerator represents how much a vector's direction deviates after being carried by parallel transport once around a single grid square of that coordinate system. Now, notice that the theta in the numerators, r, theta phi phi theta, appears as a lower index, whereas up until now we've been using r, theta phi phi theta, with theta as an upper index. Let's look at why this is. Gaussian curvature k is meant to be, on the two-sphere, an invariant quantity. Its value should come out the same no matter which coordinate system, which ruler, you use. To construct this invariant, we'll see that there's a problem with using the Riemann tensor in its upper index form. The non-zero upper index components on the two-sphere, r, theta phi phi theta equals sine squared theta, r, phi theta theta phi equals 1, are actually already corrected for the specific distortion of the coordinates, latitude and longitude, we happen to be using. Let's confirm this explicitly. Using the rule for raising and lowering indices with the metric, the upper index Riemann tensor components can be written as the upper index Riemann tensor turns out to be the lower index Riemann tensor after it's been corrected by the metric. Both r, theta phi phi theta and r, phi theta theta phi come out to sine squared theta. This means that the lower index Riemann tensor is the physical quantity representing the raw, uncorrected deviation. Let's take a look at r, phi, theta theta phi equals g phi phi, r, phi theta theta phi. Here, the factor g phi phi equals 1 over sine squared theta. The reciprocal of the horizontal width has already been multiplied in beforehand. This is where the mathematical forbidden move of 1 over 0 equals infinity arises at the North Pole. If we take the limit as we approach the North Pole, theta approaches 0, the following collision occurs within the expression. The problem, while the expression formally keeps returning 1, the instant we actually set theta equals 0, exactly at the North Pole, the left-hand piece hits 1 over 0, division by 0, and completely breaks down. A well-behaved limit, 0 divided by 0, using the lower index tensor. On the other hand, the formula for the coordinate invariant Gaussian curvature k is built, from the very start, entirely out of clean lower index components. Taking the limit as theta approaches 0, approaching the North Pole, we get in this way, when the speed, or order, at which the numerator and denominator each approach 0 matches exactly, the indeterminate form resolves cleanly, and we can define a correct, well-behaved value without any trouble at all. For this reason, it is the lower index Riemann tensor that gets used in the formula for Gaussian curvature. The dimensions of the lower index Riemann tensor. So far, we've been treating the constant, r, in the metric of the two-sphere as 1. Let's now look at the metric in its original form. If we compute the lower index Riemann tensor for a sphere of radius r, it works out as follows. Here, since the radius, r, has units of meters, r squared has units of meters squared. Since sine theta is dimensionless, the lower index Riemann tensor has units of meters squared. Incidentally, the upper index Riemann tensor, in the polar coordinates, theta, phi, turns out to be dimensionless. This is another reason it needs to be the lower index version. Three. What Gaussian curvature, numerator over denominator represents. So far we've worked out the physical meaning of the numerator and the denominator individually. Now let's think about what the whole expression, numerator over denominator, physically represents. To do that, we need to understand the physical meaning of the word curvature in Gaussian curvature. This can be thought of as the two-dimensional counterpart of the left-hand side of the Einstein field equations, which deal with higher dimensional spacetime, though the method of derivation and the precise definition differ. For that, we need to compare it against the traditional, classical definition of curvature itself. Gaussian curvature is defined using the radius of curvature at that point, in other words, the radius, r, of the sphere that fits most snugly against the surface at that point, as follows. Its units are 1 over meters squared. A sphere with a small radius, a ping-pong ball, for example, curves sharply and abruptly. Since r is small, k equals 1 over r squared comes out large. The degree of curving is strong. A sphere with a large radius, the Earth, for example, curves only very gently, which is precisely why we perceive the ground as flat. Since r is large, k equals 1 over r squared comes out small. The degree of curving is weak. Two definitions, one curvature. Let's check whether the two expressions we've derived so far actually agree. K equals 1 over r squared. The traditional definition of curvature, the intuitive definition coming from the radius of curvature. K equals r theta phi phi theta over g theta theta, g phi phi, minus g theta phi squared. The formula, computed from the Riemann tensor and the metric. These two are not separate definitions, rather, they represent the same single quantity k, arrived at via two different paths. Let's first check whether the units agree. First, let's line up the four non-zero Riemann tensor components with an upper index. Here, the difference in sign is simply a matter of convention, the order of parallel transport, or the order of covariant differentiation. For the remaining two components as well, once we lower the index to express the raw deviation as a tensor with all lower indices, both turn out to be r squared sine squared theta. Since we're now working with a sphere of radius 1, this becomes sine squared theta. Since the components of the Riemann tensor on the two-sphere are all the same value, up to sine, from here on we'll do our calculations using r theta phi phi theta. The units of the denominator of the formula work out to meters to the fourth, the square of an area. The lower index Riemann tensor in the numerator represents the amount of deviation after going around a loop, with units of meters squared. Let's write out each expression along with its units. This confirms that the units agree. However, This only guarantees that the two quantities are the same type of quantity. What we need to show next is that the actual numerical values agree completely. This confirms not just that the units match, but that the values agree completely, k equals 1 over r squared. If we substitute r equals 1, the unit sphere of radius 1 that we originally started with, into this general formula, k equals 1 over r squared, we get k equals 1. Gaussian curvature of the two-sphere k equals 1. In this way, the two-dimensional inhabitants were able to find that their space has the same curvature, k equals 1, at every point. If they knew that, at the end of a long journey, they'd return to the same point they started from, then, with these two facts together, that the curvature is constant and that going all the way around brings you back to where you started, they could, for the first time, conclude that they live on the surface of a sphere. The work we did today, extracting Gaussian curvature from the Riemann tensor within the small world of the two-sphere, is, in fact, a miniature version of the very same work Einstein carried out on the vastly larger stage of the entire universe, to uncover the true nature of gravity. The spacetime curvature that is the source of gravity. If Gaussian curvature is a tool specific to two dimensions, then the Ricci tensor and Ricci scalar, which we'll learn about later, derived from that same Riemann tensor but extended to apply in higher dimensions, are its more general successors, carrying forward that same spirit. And it is precisely that successor which forms the left-hand side of the Einstein field equations itself.